Welcome to this lecture on the Hungarian method. Imagine you are managing a small business with 3 employees and you have 3 specific tasks that must be completed today. If you have 20 employees and 20 tasks, the number of possible combinations is larger than the number of stars in the universe, making guessing completely impossible. Today, we will learn a brilliant mathematical shortcut that finds the absolute best pairing without having to check every single combination. Now that we understand the scale of the problem, let us look at how we solve it. The Hungarian method is a step-by-step algorithm used to solve what mathematicians call the assignment problem. This is simply the challenge of matching items from 2 equal-sized groups, like workers to machines, at the lowest possible cost. The method relies on a very clever logical trick. If you subtract the same amount of money from every contractor's bid for a specific job, the contractor who was the cheapest originally will still be the cheapest. By strategically subtracting values, we create glowing signposts of zeros. To understand how this works mathematically, we first need to define our goal using a formula. We arrange our costs into a grid where each row represents a worker and each column represents a job. This formula calculates the total cost, which we call Z, that we want to minimize. The variable n is the number of workers. The symbol C sub ij represents the specific cost of assigning worker I to job j. Finally, x sub ij is our decision variable. It acts like a light switch, equaling 1 if we assign the worker to the job and 0 if we do not. If costs increase, z increases. This formula we just saw leads us to an important question. How do we ensure everyone gets exactly one task? We cannot just assign everyone to the cheapest job. We have strict rules to follow. This first rule ensures that every single worker gets exactly one job. The summation symbol tells us to look at a specific worker I and add up all their job assignments across every job j. Because the total must equal 1 and our decision variable can only be 0 or 1, the worker is forced to take exactly one job and no more. If this sum were greater than 1, one person would be doing multiple jobs. Now that we have restricted the workers, we must apply the same logic to the jobs. This second rule is the mirror image of the first, ensuring that every single job gets exactly one worker. Here, we look at a specific job J and add up all the workers I assigned to it. The total must again equal 1, meaning the job is completed by one person and it is not left empty. Together, these two rules guarantee a perfect one-to-one matching between the two groups. If we increase the number of jobs, we must equally increase the number of workers. Before we move on, let us see this with a concrete example. Suppose we have 3 workers and 3 jobs, and we are given a cost matrix representing how many dollars each worker charges. We want to find the cheapest way to assign one worker to one job. We start with our original matrix. The first step is row reduction. We look at each row individually, find the smallest number and subtract it from every number in that same row. For the first row, we subtract 9, for the second 9, for the third 8. This creates a new matrix with at least 1 0 in every row. Continuing with our problem, we now have zeros representing the relatively cheapest options for each worker. The next step is column reduction. We look at our new matrix, find the smallest number in each column and subtract it from every number in that column. In the first column, we subtract 0, in the second, 1, in the third, 0. Now we have a matrix with zeros in both rows and columns. The next step is to test if we have enough zeros to make a perfect assignment by drawing the minimum number of straight lines needed to cover all the zeros. Now that we have drawn our lines, let us find the final result. We used exactly 3 lines to cover all zeros. Since the number of lines equals the number of rows, which is 3, we have reached the optimal solution. To make the final assignments, we look for rows or columns that only have a single 0. Worker 2 must take job 1, worker 3 takes job 3, leaving worker 1 with job 2. Looking back at the original matrix, we add the costs of 10, 9 and 8. The absolute minimum cost is $27. This diagram visually represents the final solution we just calculated. On the left, we have our 3 workers, and on the right, our 3 jobs. The green arrows show the optimal one-to-one matching we discovered. Notice how no 2 arrows point to the same job and no worker has more than 1 arrow leaving their node? This perfectly satisfies the mathematical constraints we defined earlier, ensuring every task is completed by exactly one person at the lowest possible cost. Now that we have seen a perfect scenario, what happens when things do not align so easily? Sometimes the basic row and column reduction does not give us enough zeros to make a full assignment. When we draw our lines and find that the minimum number of lines is less than the number of rows, we have not reached the optimal state. To fix this, we must modify the matrix to create more zeros. We do this by finding the absolute smallest number that is not covered by any line, subtracting it from all uncovered numbers and adding it to the intersections. Let us apply this modification technique to a slightly larger problem. We are given a new original cost matrix for 4 workers and 4 jobs. Just like before, our first step is row reduction. We find the smallest number in each row and subtract it, giving us our row-reduced matrix. Next, we perform column reduction by finding the smallest number in each column and subtracting it. This gives us a matrix with zeros, and we are ready to test if an optimal assignment is possible. Continuing with our 4x4 matrix, we try to cover all the zeros with the minimum number of straight lines. We find that we can cover all zeros using only 3 lines. Since our matrix has 4 rows, 3 lines is not enough, meaning an optimal assignment is not yet possible. We look at all the numbers not covered by any line and find the smallest, which is 1. We subtract this 1 from all uncovered numbers and add it to any number where 2 lines cross. Numbers covered by only 1 line stay exactly the same. We have created new zeros, so we try to draw lines again. Once again, we find that all zeros can be covered using only 3 lines. Because 3 is still less than 4, we are still not done. We must repeat the modification step one more time. We look at the uncovered numbers in our current matrix and find the smallest is 2. We subtract 2 from all uncovered numbers and add 2 to the intersections where our lines crossed. This shifts the values around again, hopefully creating a pattern of zeros that will allow a full assignment. Let us try drawing lines one last time on this newest matrix. We find that no matter how cleverly we place our lines, we absolutely must use 4 lines to cover them all. Because the minimum number of lines is now equal to 4, we have finally reached the optimal state. We pick our assignments by looking for rows or columns with only 1 0, assigning worker 4 to job 3, worker 2 to job 1, worker 1 to job 4, and worker 3 to job 2. Adding the original costs, the absolute minimum total cost is 49. Now that we have solved these matrices, why does this mathematical process matter in the real world? It is used everywhere behind the scenes to make our lives more efficient. When you request a ride on an app like Uber, the system uses a variation of this logic to match you with the closest driver, minimizing the total wait time for everyone in the city. Hospitals use it to assign nurses to different wards based on their skills and shift preferences, ensuring the best possible care at the lowest scheduling cost. Without this method, computer systems would freeze. To summarize our lecture, the Hungarian method is a powerful and elegant tool for making the best possible one-to-one matches. By systematically subtracting minimum values from rows and columns, it reveals a path of zeros that points directly to the cheapest solution. We also learned that when basic reduction is not enough, matrix modification forces the numbers to reveal the optimal pairing. Whenever you need to pair up resources efficiently without checking millions of combinations, this algorithm provides the perfect mathematical strategy. You now understand the complete foundation of the Hungarian method.